Tom Blenkinsop is a professor at the School of Earth and Environmental Sciences, Cardiff University. His research interests are in deformation and fluid flow and applications of structural geology to natural resources. He works extensively with the exploration and mining industry, mainly on copper, gold, and IOCG deposits. Tom graduated from Oxford University and completed an MSc at Imperial College before undertaking his doctorate at Keele University and postdoctoral research at the University of California, Santa Barbara. He was a professor at the University of Zimbabwe and then at James Cook University in Australia, where he was director of the Economic Geology Research Unit. He has published over 150 papers and a textbook on deformation, microstructures, and mechanisms. Recently, he has developed an online course in structural geology for exploration and mining. He is also on the editorial advisory board for the Journal of Structural Geology and is an editor for Ore Geology Reviews. And with that, Tom, I hand over the virtual floor for you and you may begin your talk. Thank you.
Well, thank you very much. And I would like to start off by saying thank you very much for Ore Deposits Hub for inviting me to give this talk. And it really is truly amazing to see where all of you are coming from all over the world. So good morning or good afternoon, wherever you are, and thanks very much for joining. I'm going to start with this slide to acknowledge that a lot of the material I'm going to present in the next half hour is based on a paper in Reviews in Economic Geology, a special publication with my co-authors, who are listed here on the slide. So I'd like to acknowledge them to begin with. What I'm going to talk to you about is deformation zones, and specifically the way in which deformation zones form networks and the sorts of networks which we can find and therefore use in an exploration sense, so network geometry. We then go on to consider another aspect of networks, connectivity, before taking a somewhat speculative view of the relationship perhaps between percolation theory and natural resources. And here I'm going to stray a little bit from the strict ore deposits purview of this group into including hydrocarbon resources as well. But I think they illustrate the same sorts of principles. So let's start off with deformation zones as such. As everyone knows, this sort of style of deformation zone is remarkably common in hydrothermal ore deposits. What I mean is the style in which we see some combination of discontinuous deformation dominantly at the top of this slide and continuous deformation dominantly at the bottom. That sort of mixed style of discontinuous and continuous deformation in which we may have veins, fractures, breccias with alternating or intermixed with strongly foliated rocks with more continuous styles of deformation. It tells us something very important, and that's been long recognized about how hydrothermal ore deposits have got a particular combination of strain rates, pore fluid pressures, and stresses, which lead to an alternation of continuous and discontinuous styles of deformation. And that's illustrated for you from several examples from Sunrise Dam in Western Australia, which I'll be referring to quite a bit, and also from Gator Gold Mine in Tanzania, and a couple more examples, Cornishman and Tropicana from Western Australia. So what we've been just looking at is summarized in the middle row of this sort of schematic diagram, which attempts to show in a hierarchy of scale what sort of structures are important in hydrothermal mineralization, starting with individual features such as fractures or faults, veins, stylites, or fabrics, the way they come together in a particular deformation zone, a discrete deformation zone, which has some combination of discontinuous and continuous deformation in it, faults to shear zones, that sort of spectrum. And then on the larger scale, the way in which these deformation zones themselves come together to form a network. This is the subject of the talk really today. The geometry of the networks which are formed by linking up deformation zones. And again, we can consider this in a spectrum from very discontinuous styles, for example, represented by stockworks, through to networks of continuous deformation zones. And the next slide is an attempt to sort of summarize, to introduce that via the concept of multiple fault sets. This is one particular example of very discontinuous deformation zones or faults, in which our understanding has evolved quite considerably in the last 20 or 30 years from the picture on the left, which is very familiar from sort of introductory textbooks on structural geology, in which we have a pair of conjugate faults arranged symmetrically about the principal stresses, to the picture on the right, which shows that actually in many cases we don't have just two orientations of faults, but possibly four or even more in a single deformation event. These are multiple fault sets, and that they're organized about the bulk strain axes rather than the stress axes. This is a very important shift in concepts really about deformation zone networks, that they are more easily relatable to strain rather than stress. So we can take that a step further and arrive at some sort of schematic diagrams like these. On the right-hand side are diagrams which are similar to the ones you saw in the previous slide, which show multiple fault sets. And what they show is that the actual geometry of those multiple fault sets will depend on the bulk strain, depending on whether we have at the top constrictional strains or at the bottom flattening strains. And we can take this example over into the world of continuous deformation to also observe that in prolate or constrictional strains, we have a geometry of shear zones which typically isolate rod-like or elongate bodies of rock between them, sometimes called lithons. Whereas in the flattening case, we have a network which is arranged so that we have lozenges or pancake-shaped lithons between the network of shear zones. And this concept has been understood for shear zones for really quite a long time, certainly as long as it has faults, and it goes back to the work of Denis Gapet and Peter Cobbold and others many tens of years ago. But it's sometimes, and surprisingly, overlooked as an important tool that we can use for exploration. Well, I've made that bold statement, but so I suppose I better back it up, hadn't I, with some examples. And it is surprisingly hard to come across some clear examples of this sort of network control on ore bodies and ore deposits. And I think the reason for that is largely that this scale of linking of deformation zones has been overlooked, although it's been well understood in a sort of academic, theoretical sense by structural geologists for a long time. It has not yet been widely applied to exploration. So let's have a look at some examples in the next few slides. And I want to start off by making another acknowledgement here. Having given a similar talk some weeks ago, I was contacted by Francois Robert, who sent me some wonderful examples from his work and others that he knew of deformation zone networks, which are linking up in the ways which I've been showing you in sort of theory in the previous few slides. So here is one example from the Dumont mine, the work of Belkabir and others, in which careful level mapping has shown this anastomosing network of shear zones, which looks awfully like one of the schematic diagrams I've shown you. And when you come to look at these shear zone orientations in more detail, you see that they're not simply forming a conjugate set, that they are actually forming sets in several different orientations that are linking together very much in the schematic way shown in the previous slides. So there's an example in practice. Another one in the next slide, in fact, this is the first one that I was widely aware of from the work of Benoit Dubé and others in the Norbeau mine in Quebec, in which they identified that within a particular mafic sill, there were a variety of orientations of auriferous veins, and they also related these multiple different orientations to a single kinematic picture, which they deduced using Wallace's method. So this was a nice example indeed of how the deformation zone network came to be organized around principal strain axes. Well, we haven't finished yet. So another one I'm grateful for to Francois for pointing out is his own work from the Perron deposit. And in this case, an interesting arrangement of intersecting deformation zones with that mixed continuous and discontinuous style that we saw is so common, all of them intersecting in this case, one common axis, which was equated by Francois with the Y or intermediate principal strain axis, with the X and Z forming perpendicular to that within the normal to that common intersection direction. So another lovely example of how deformation zones actually organize themselves on a larger scale to reflect the principal strain axes. And then finally, another example again from Francois's work from the Cisco gold mine here, in which again, a similar variety of different orientations of auriferous reefs in shear zones, which can be related to a common extension and shortening direction, and in other words, strain axes. So I think the evidence is now becoming quite compelling that we can do this if we map sufficiently carefully, and we also look at kinematics. We can see that what appear to be very many different and perhaps arbitrary orientations may in fact actually belong to a common deformation with a common strain field, and that would have tremendous predictive possibilities as well for exploration. So I think that's a major conceptual advance, which, as I said, has been around for a long time, but not necessarily widely applied in the exploration industry. All right, I'm now going to move on to part 2 of the talk, in which we're going to look at networks of deformation zones. And the background to this, which is extremely clearly laid out in this paper by Sanderson and Nixon, is really derived from the hydrocarbon industry, where issues of connectivity in fracture networks are of critical importance to determine the locations and seal properties of rocks for hydrocarbon resources. And so what I'm going to do in the next few slides is simply borrow those concepts and see if they can be applied in the context of ore bodies, ore deposits. On the left here, you see a map of a fault network, in fact, a gold-bearing fault network, with a sampling circle in purple around it. And the idea of this approach is to divide the deformation zones, in this case fractures, into intervals which are separated by nodes where one fracture crosses another, or endpoints. So we can actually distinguish 3 different types of nodes, which are called I, Y, and X. An I node is what happens at the end of a fracture, where it ends. A Y node is where one fracture joins another and stops. And an X node is where 2 fractures cross each other, in blue in this case. Now, fairly obviously, the more X and Y nodes there are, the more connected the network is. And we can use a parameter called the connectivity of branches, which is given by this formula up here, which simply involves us counting within our sample circle the number of Ys, the number of X's, the number of I's, and deriving an index of connectivity. There are many advantages of analyzing networks by this branch approach, which is not the traditional way of doing things, but it is extraordinarily simple and powerful. And we can arrive at, therefore, this index of connectivity just by counting the number of the different types of node. But it's not just the connectivity we might be interested in. We can, for example, imagine 2 networks which have got the same connectivity values, but very, very different intensities of fracturing. So we also need a measure of the intensity of the branches. And there's a simple way to do that with a circular scan line like this, which is to count the number of fractures which intersect the edge of that scan line, n, divided by 4 times the radius. That gives us the intensity. So we have those two parameters, intensity and connectivity. And we're going to have a look at how they may relate to each other in just a minute. So before we go on to that, let's just finish off on this slide by presenting the triangular diagram that Sanderson and Nixon produced, which shows the number of I nodes at this apex of the triangle, Y down here and X over here. And this diagram is contoured by the connectivity as established by that formula here. And you can see the contour values increasing towards a maximum of 2 along the Y-X boundary at the bottom for a fully connected network. This particular example plots here in the purple triangle here between a connectivity value of about 1 and 1.3. So it's relatively unconnected. And that may or may not be a good thing from an expression point of view. That's what we're going to explore in a next few slides. So I'm going to take you now to the Yilgarn Craton and talk about Sunrise Dam in the eastern part of the Yilgarn. At the moment, claimed to have a resource of 4 million ounces, but at times Sunrise Dam has actually exceeded the production of the Golden Mile at Kalgoorlie. So it's Australia's premier producing gold mine at times. And when we look at a view of the mine in a cartoon form to show the different ore bodies underneath the open pit here, you can get an impression of why it's been such a phenomenally productive mine. There are many, many different ore bodies in different orientations under different parts of the open pit. The scale here is at least several kilometers from one end to the other. And each of these has produced significantly different types of ore with different structural controls. So it's a very complicated ore deposit as a whole, and it's got evidence of multiple stages of mineralization and reactivation like many giant or large ore deposits. I'm not going to go into any of those details. All I'm going to do is to direct you to the Astro Lode here and one particular development drive in the Astro Lode, which we're going to have a look at in more detail. Here's the map of the face of that drive, and you can see that mapped onto this photograph are a number of veins, quartz carbonate veins, many of which are auriferous indeed, and can be divided up into 3 major sets depending on their orientations. In fact, this looks, doesn't it, rather like a stockwork. It's almost a stockwork, really, of gold-bearing veins. And it's pretty well an ideal situation to start to think about connectivity and intensity of networks. So we can take a map like this, and indeed we can take a circular scan line, prop it up here on the map and count our number of I, Y, and X nodes. And by moving that circular scan line along the face, we can do this for different places along the development drive, and we can compute the values of connectivity and intensity for each place along the drive. So that is what is shown in this graph here, in which we're plotting the connectivity against the intensity. And what is interesting about that result is that there's no obvious or no relationship. And this bears out what I was saying earlier, that you need both the connectivity and the intensity measures to fully characterize the network. Well, again, is this really of any practical use? And I want to direct you now to the work of Turlin and others in 2019, the Choo Choo gold deposit, in which they looked at connectivity of different types of veins on a core scale and correlated that with gold grades. So in the background here, you can see in the gray colors, the grades, the gold grades, and in the white dots joined by the black line here, you can see the fluctuations in gold grade, in connectivity of the quartz veins. And there is a first order correlation between the higher connectivity and the higher gold grade. So I think this is a very exciting and promising development, which certainly needs more work to test ideas about how it can in fact be used in a predictive sense. But here's a strong clue to begin with. So now we're going to move on to the third part of the talk, a little bit more speculative this time, and talk about percolation theory. So percolation is the study of connectivity of random media, and that word random is important. There is always in percolation theory a random component. It may be the way in which pores are arranged in rocks, it may be the arrangement of fractures, but in some ways, in some sense, percolation theory is able to deal with this random or stochastic element. And there are different types of percolation theory, site bond or continuum percolation. Continuum percolation is particularly relevant to fractures, but I'm more going to be talking about site percolation in the next few slides. And what this means is that if we consider a network represented by these blank cells, we may fill it with some cells containing, for example, an ore deposit, or it could be fluid in a porous network. And we're going to find, as we start to fill up more and more of those cells, that two or three of them are going to cluster together to form a continuous connected so-called percolation cluster. That's a very important concept in percolation theory. So my proposal for you today is that we can actually think of the crust as some sort of percolation network. We've got fluids flowing perhaps through fractures or pipes and being deposited somewhere to form ore bodies, and those ore bodies represent a section through a percolating network in 2D section. So with that hypothesis or proposal, what else can we do? Here are two percolation networks viewed in as it were, in the section of a 3D example, like in the previous slide. And on the left-hand side, you see a proportion of cells of 0.26, which are filled, the red ones, nominally representing, say, a deposit. 26% of those cells are filled. On the right-hand side, you see a higher proportion, 37%, 0.37 of the cells are filled. And at this point, something very special has happened to the network to distinguish it from the previous example. It is possible to trace, in this gray line, a connected pathway through the whole network, allowing for connections to be established, say, at diagonals as well as directly between faces, adjoining faces. And so that marks a critical step, as a major change from the previous case, which is called the percolation threshold. And this is an example of a network which is at the percolation threshold. Now, in practice, it is actually quite difficult to apply this rather abstract geometry to a natural map of ore deposits, especially as we would then have to deal with the awkward business of defining what the area of an ore deposit is and somehow converting that into this rather regular network of squares. So it's rather easier to look at another parameter of these sort of networks, which can be easily measured without having to make those awkward sorts of decisions. And that's called the fractal dimension, here D. The D value at the network which is less than the percolation threshold is 1.56, this example. In this example, for the network above the percolation threshold, it's 1.9. And the good thing about this approach is that we know these values from theory. we know the fractal dimensions from percolation networks, both in 2D and in 3D at the percolation threshold. And we know the values below and the values above the percolation threshold. So we can measure whether the network is at percolation threshold by measuring these fractal dimensions. Okay, again, we would want to see if this really has got any legs to help us in a practical sense. So I'm going to look at gold deposits, hydrothermal gold deposits on the Zimbabwe craton here showed. And like any pattern of gold deposits on this sort of scale, we recognize that there are clusters, geologically controlled clusters of deposits. But from our point of view, the question is, can we treat this as a manifestation of a network and measure the fractal dimension, which we will in fact do. And this is where I'm going to stray a little bit from our strict ore deposits context. I'm also going to show you some results from gas wells in Pennsylvania, unconventional or fracking gas wells in Pennsylvania, which of course have made such a huge difference to the energy scene in the world on a global scale by establishing a large degree of independence for the USA from other supplies of hydrocarbons. Now, actually, I started to get interested in this topic when I started to look at maps like this and think about what the impact of such an incredibly dense network of gas-producing wells might be on the landscape. And I had a quick look at Google Earth, which can give us some clue to the answer. So I'm now going to show you now how, when you zoom in to that area of Pennsylvania on Google Earth, you can see the sort of impact that the fracking world has had on the landscape. Each one of those little clearings in the forest there is a gas well, gas producing well. So scattered all over the landscape. And of course, the reason they're there is because below several thousand meters below the surface of the Earth is the Marcellus Shale, which is a perfect example of an unconventional gas hosting horizon, which can be fracked and gas can be produced from it. So I also thought it'd be interesting to have a look at another very indirectly related topic to ore deposits, and that is geothermal energy. So here's a map of Oregon in which we're looking both at geothermal wells using geothermal energy in brown and volcanic vents in red. Different patterns, but and obviously the wells are clustered around centers of population, whereas the volcanic vents themselves show a more geologically controlled pattern. So all of those things can be analyzed in terms of their fractal dimension, and these are the results from that analysis. And they're ranked from the low values at this end of the table, which apply to the gold deposits in Zimbabwe, to the high values at this end of the table, which pertain to conventional gas wells, with the unconventional gas wells somewhere here in the middle. And basically, the simplest way to interpret these numbers is that the lower the number, the higher the degree of clustering. So the gas wells are relatively unclustered, the gold deposits are highly clustered in that scale. But that's really not so much the point here. The point is that all of those numbers are well less than the percolation threshold for 2 dimensions. So we can conclude that the deposits represent a network which is less than the percolation threshold. Now, does that surprise anyone? Perhaps I've given the impression that more connectivity is better. But in fact, if you think about it, it's probably the opposite. If any of these were completely connected networks, the fluids would be flowing completely from one side to the other through them, and there would be no possibility of forming an ore deposit or a gas deposit. So actually, it's no surprise that these are unconnected networks. Mineralization seems to, in fact, require there to be a degree of disconnection in the network in order for it to form a deposit. That could be one interpretation of these results. The good thing is also that having established these fractal dimensions, they can be used directly to predict the number of resources in a particular area. So they have a practical consequence. So all I'm saying really is that the Earth is like a coffee percolator. We heat up our hydrothermal fluids, we flow them through the rock, they pick up their mineralizing charge, and then they deposit somewhere else. Coffee percolator seems like a great analogy for what's going on in hydrothermal mineralization, and percolation theory can deal both with the coffee percolator and the situation in the Earth. So I'd like to just finish off with one final slide here on percolation theory. Again, this idea has been around for a while, and Steve Cox first thought or talked about it in this paper in 1999, where he was illustrating how a network might have arrived at the percolation threshold. You can see this solid black line crossing from one end, the bottom end of the map or cross-sectional area to the top end. You can see that there are a number of elements which are completely disconnected. These would have I nodes at either end. And you can see there's an interesting third category of elements in this network which do terminate in I nodes, but are connected to the through-going fracture network. Now, these are sometimes called dangling elements in percolation terms. And what is really interesting is to speculate that actually it might be these elements of a percolation network which are most important for mineralization. If you're on the through-going fracture network, the fluids are just charging through without the chance to deposit. If you're on an isolated network fracture, you're not going to get access to significant quantities of fluid or mineral content. However, if you're on a dangling element, you may be both connected to the fluid pathway, so that a lot of fluid is actually flowing through or past the fracture, and you may be in a situation where that fluid is interacting with adjacent host rocks or other fluids to facilitate the precipitation of its mineral charge. So it could be the dangling elements that are really important in a percolation network. And that, of course, might find an echo or a reflection in the well-known propensity of large mineral deposits not to lie directly on the major through-going crustal scale shear zones, but on so-called second order or third order fractures which lie adjacent to them. I think that's an interesting speculation that we might be able to now explain that observation with this sort of percolation theory approach. So I'm just going to finish off now with a quick summary of some of the main points from talk. I think I started off by trying to convince you that not only do deformation zone networks have predictable geometries which are related to the bulk strain, but that there are now a number of cases in the literature where we can demonstrate this for mineralized deformation zone networks. Topological analysis, the analysis of branches and their connectivity and intensity, is a promising approach which we can certainly apply if we have detailed maps of fracture or mineralized networks. And then the more speculative part of the talk, in which we attempt to use percolation theory to understand distributions of natural resources. So I'll leave it at that with some references there to the main papers which were quoted, and I'm looking forward very much to having a bit of conversation, and I can see there's already lots of interesting questions. Okay, so John says the impact of those wells looks pretty minimal, far less impact than the agricultural clearing activity, and likely producing vastly more in revenue. That's a good point, John. Yes, they are small clearings, aren't they, in the forest there? I was just curious about how dense they must be to have that number of wells. Alex has asked, what happens if you consider the entire fluid structure system rather than the economic deposit? This may show trends or camps have more connectivity. There's also the fourth dimensional connectivity through time, and variations in this across the network is highly likely in dynamic systems like hydrothermal systems. Good points, very good points. Yes, of course, one would really love to be able to untangle the whole fluid structure system rather than the economic deposit. And maybe there are places where you can do that, but I think it's still very difficult really to know, even if you can map out a zone, a network of deformation zones on a large scale, whether they were all active during the mineralizing event. So that's one problem. So as you allude, the time, the connectivity through time is really a big issue here. And I should say, by the way, that one of the advantages of the Sunrise Dam system is that we can prove from cross-cutting relationships that all of those veins in that network were simultaneously active. They've all got similar vein fillings, and they mutually cross-cut each other. So that was a big advantage of using that particular data set. But certainly all of those points about thinking about the evolution through time and the dynamic system is very important as well. Okay, so Alannah, can you comment on the role of clogging and sealing in repeated fracturing with respect to fractal dimensions and connectivity? As geologists, we look at one snapshot in time, surely the timing of fractures is also critical. Absolutely. This is similar to the point that was being made before, the dynamic nature of these networks, their evolution through time, and the fact that we, in the end, are only looking at a final view of the network. But I think it does still make sense to think about the network evolving in terms of percolation theory, because there will presumably be a time when that percolation threshold is exceeded, and that should presumably also very radically change the mineralizing system. And as I've hinted, maybe once that percolation threshold is exceeded, then maybe the potential for mineralization is very much reduced in that particular area. And maybe we then need to look on to another part of the percolation system to see as it evolves, see how it evolves with time. So yes, timing and dynamic effects are always a very difficult problem to deal with. And it could be that, as you, Alannah, indicate, that by sealing off fractures, the network doesn't evolve straightforwardly into across a simple percolation threshold. In fact, it may alternate across that threshold a number of times because of the sealing effects. So that's something, definitely a complication to try to get to grips with.
Hi Tom, thanks very much for that answer. I don't know if Robin, you can keep reading from the chat. We also have some questions on YouTube, and Robin and Charles can also help you filter. I know there's a lot coming in. So maybe, I don't know, Robin or Charles, if you want to jump in there as well. There's a few more questions for host to read, and I'll send you over the ones from YouTube.
Sure. So we have a question from Devito Predictor, who wants to know, Tom, how should they apply fracture network analysis to their sort of study and exploration? Does it have to be done at the outcrop scale, or can you do this in thin section, or perhaps on any other sort of analytical technique? And when you identify these fractures, do you have to discriminate which are tectonic, or do you just include
Okay, well, there's some great questions to think about there. My instinct as far as scale is concerned is that this is potentially not particularly relevant to thin section scale. At least I've never tried it at that scale. And perhaps the underground face would be about the smaller scale that one might do this. And it might also be quite applicable at larger scales, sort of regional scales. But of course, you do always face the problem, which we've alluded to many times. Are we really looking at a map of fractures which were actually open during mineralization? That's always a critical thing to try to find and to justify the inclusion of those fractures. So definitely not any fracture, definitely probably not exfoliation joints, because those were very unlikely to have been part of the mineralizing network. We want as far as possible to get a map or deal with a map which represents the network at the time of mineralization. So I would say it's extremely important really to have a quality control and filter out some of the fractures that you would map anyway, if you map all fractures. Okay.
Okay, Tom, we have a question from YouTube for you. Are there any resources or guides available for an explorationist looking to do some basic topologic analysis on their network? Are there any red herrings or things to look out for in particular?
Okay, well, that's a great question. And yes, there are resources now. In fact, a couple of free resources allow you to analyze networks on maps. And two of them are FracPack by Dave Healy, which has been around for a while. And also the second one is Network GT, which is an ArcGIS-based plugin, which is also being developed actually for QGIS at the moment. So those resources do exist. So yes, they are available. Sorry, the second part of that question was?
Are there any red herrings or things to look out for in particular?
Yes, well, I think we have already touched on the big red herring, which is the existence of fractures which were not part of the mineralizing network. Either they predated it and were not reactivated, or they postdate it. So that is a big red herring to be very careful of.
I think we lost you again, Charles.
Oh, no. Okay.
Question is comment between mineralized and barren fracture vein networks.
Okay, so I think if I understand it, the question is how to distinguish between mineralized and barren fracture networks? Is that the hint? What the question is getting?
Yeah,
at?
perhaps also you could lead into like, how does that feed into our connectivity system, or like, I guess that's such an important aspect here if people are mapping in the field, the different to distinguish those aspects.
Mm-hmm. Yeah, it is interesting. This question is coming back time and time again from different sort of points of view, because it is such a difficult and important question. I think that one clue about whether the fractures belong to a network which was sim mineralization is the establishing cross-cutting relationships. I think, you know, actually counting very carefully the fractures of one set that cross or terminate at fractures of another set, and seeing whether those relationships are mutual or whether there's a consistent timing relationship is something we perhaps don't do enough of. And given that we had one fracture which is clearly part of the ore mineralizing system, and we can characterize it as belonging to a set which is cross-cut by another set of fractures consistently, which are later, would give us a clue that we perhaps need to distinguish those two fracture sets. Or alternatively, the situation like in Sunrise Dam, when veins which we can clearly characterize as gold bearing are mutually cross-cutting and cut by other veins, would indicate that those veins are part of the mineralizing system. So looking at cross-cutting relationships is tedious, sometimes difficult, but something that we should really pay attention to. The other clue, of course, is alteration and vein filling. I'll put those things together. Looking at the alteration systems, the alteration mineralogy, and the vein fillings, of course, gives us a great clue as to the timing or the different generations of veins. So you would ideally want to have the same components of the vein fill, the same alteration system in the system of fractures or veins that you're mapping to demonstrate a syn mineralization network.
Very good. Thank you, Tom. I have a question here from Dr. Raju, PVS. Raju, would you like to unmute yourself and ask the question? Okay, maybe not. So the question was, does viscosity and fluid pressure play a role in connecting high grades and mineralization?
If we were to get into the detailed physics of the fluid flow, inevitably it would. Perhaps it's even more directly important in studies which are trying to work out whether pressure or temperature controls are important in precipitation mechanisms. So those physical properties of fluids undoubtedly are very important. I've just seen in the chat a question from Julian Grodzicki, which I would really like to highlight if that's okay, because I find it very interesting. Julian says that he's a geology student who became an electronics engineer, and he deals with network theory and wonders if it can be translated into mechanical dashpot models and continuum mechanics and applied to give a theoretical basis for your work. Well, that's a really interesting question, because actually percolation theory itself started off from a completely different viewpoint, and it was applied to all sorts of different phenomena. For example, forest fires were studied using percolation theory. What I'm trying to say is that I really like this question, because I think we can learn an awful lot by this sort of cross-disciplinary approach, and perhaps trying to put a mechanical spin on network theory and getting continuum mechanics models involved is definitely a very fruitful way to go. I did mention briefly there is the continuum style of percolation theory or approach to percolation theory, which is actually what discrete fracture DFN, discrete fracture network modeling does. So there's a very strong crossover there between continuum mechanics and percolation theory. So yes, Julian, thanks for that question. And in general, the idea of taking from one branch of physics or chemistry and applying it another is a great thing to think about.
Excellent, thank you. I just want to let everyone know that I've dropped the link to the certificate of attendance into the chat. And I have another question for you, Tom. There's very many. If I understood correctly, you mentioned that connectivity doesn't favor the formation of ore slash gas deposits because the fluids flow out. But in some deposits, connectivity to the surface seems to be a critical process, not only to flush out the fluids, but also to the incursion of meteoric fluids. Besides, temperature and pressure also play an essential role. Can you comment on that?
Okay. Okay. Well, now I'm going to have to be very honest. I hope that I gave a rather ambiguous impression about what I really think about connectivity and percolation thresholds and mineralization. Because on the one hand, if you think about it, I said the highly connect from the study of Turlin on the drill core, the high connectivity appears to correlate with high grade. On the other hand, I said that if we look at the fractal dimensions, these are not networks at percolation threshold. So I have deliberately tried to sow the seeds of some confusion. And the reason for that is because I think we don't know yet. We are only starting to apply these concepts of percolation theory. And there are alternative models. If you look at the Steve Cox cartoon that I showed at the end, that would have yet a different implication, because it would indicate that you could find ore deposits in the so-called dangling elements of a network which has crossed the percolation threshold. And on top of all of that, the point again and again comes back to the fact that we're looking at the final state and not the state during mineralization. So all of those are vastly complicating factors, which I hope, which don't allow me to reach very simple conclusions, I think. And basically, this is just a way of saying lots more research needed, but these are potentially promising directions.
Great, thank you. Charles, would you like to ask the next question?
Sure. Tom, I have some questions for you from Phase AKP. So they want to know if the connectivity of the structure can guide or give you an indication of the direction of the ore chute. That's part one of the question.
Okay, well, that's a really intriguing possibility. And if you looked at the Steve Cox cartoon, that would definitely be the implication. The more connected, the closer you are to the through-going pathway, the more likely you would be to approach the ore body, with the proviso that you don't want to get actually onto the fully connected structure. So you want to be in that sweet spot just adjacent to it, the so-called, secondary shear location. I think that's one potential interpretation, but the principle that you could perhaps use connectivity as a vector to that place, I think, is a very interesting possibility. Yeah.
Brilliant, thank you. And then the second part of the question asks whether spotted ores are produced from the connectivity of a structure. Spotted ores, I assume, might mean disseminations.
In the sense that if a disseminated deposit is representing some sort of Darcy-like percolation or fluid throw adjacent to a fracture, then I suppose it could be, yes, indeed, it could be related to the fracture network. Another way of looking, of course, at disseminated deposits is that they represent flow through very small scale fractures, completely distributed small scale fractures. Maybe there's something to be thought about there in terms of how those small scale fractures link up. Although I said before, I think looking at it on the very small scale is fraught with problems, not least of which is that, things get very heterogeneous at that very small scale. So that could be tricky. So those are just a few things to think about in response to that question, I guess.
Yeah, I jump in there with one, Thomas. I know you mentioned discrete fraction networks, and part of my work on larger scale VMS systems has been to try and understand fluid circulation within the oceanic crust and look at both the porous media that's hosting fractures and the fractures themselves. And one thing that has been a bit tricky is actually integrating that part of connectivity into a discrete fraction network. I mean, usually in the field we can quantify a fracture intensity, but actually taking connectivity and putting it into a model, I haven't seen that done yet, and I wondered if you have seen that done. I've looked in, like, for example, in Frackman, and also I think there might actually be a possibility in there, but also in DFN Works, which is a code that I've been using from Los Alamos. Mm-hmm. But yeah, I just wondered, have you seen it done, integrating connectivity into a stochastic generation or a fracture network?
You're reminding me of something I have seen very similar to that. I think I'm going to have to get back to you on that. But my question to you would be, given the node approach that has been outlined, could you not, for a DFN, you know all the details of the fractures. You would be able to identify those nodes, wouldn't you? So could you not take that node approach and look at the topological characteristics of the DFN just like any other fracture network?
Yeah, I guess you could do it in a way that's kind of like iterative, in a sense that knowing what you know from the field and then generating the model and then looking back and seeing, have you really matched the nodes and the connectivity? But in terms of an input parameter, I haven't seen one yet. But yeah, if you do remember what you're thinking of, please get in touch. It'd be great.
I'll make a note to try and find that reference. DFN and connectivity. Yeah, of course. The big question there would be the 3D aspect, because that node analysis is just a 2D one, and I know,
yeah, for sure,
Dave Sanderson has been thinking about that 3D aspect too. So there's probably a solution for that somewhere.
Yeah, one of the interesting things with the software DFN is that you can have both the porous media and the fracture aspects in one model, which has been really fascinating in terms of an ore system where you have a porous, like say a basalt as the host rock. So I think also that's an interesting aspect here, whether we've got flow through the matrix as well as in the fractures themselves.
Yes, the dual permeability problem is definitely an important one, and of course that might be very relevant to disseminations, mightn't it, as well?
Yeah, definitely.
Perhaps you know, the porous flow is sort of percolation at one scale, and the fracture network is percolation at a different scale.
Yeah, for sure. I mean, depending how long your fractures are and what you, yeah, I mean, the matrix is pretty small scale usually. So yeah, all really interesting. Charles, Robin, any more questions there?
I'm not seeing any more questions.
I see there's quite a few comments.
Yes.
If feel free to jump in there and read those out. It's always interesting to hear from you.
There's a comment from John Menzies about diamond drill core.
That's right, oriented core, yes.
And getting the most information. Couldn't agree more that that's a very key thing. That Turlin study, for example, was based on fractures looked at in core.
All right, great. Well, Tom, thank you very, very much for your time here. I think everyone really enjoyed your presentation. And I think we can wrap up this session. So thanks very much, and thanks to our audience.